Chapter 2.3, Polynomial Functions and Their Graphs. So in this chapter, we are now going to be looking at polynomial functions. We'll learn what they are, as well as how to identify various characteristics of them, especially how to find their end behavior and their zeros, all of which will help us to figure out how to graph them. So before we get to what a polynomial is, we're going to look at something a little bit simpler. So a power function is a function that can be represented in the form f of x equal to kx to the p, where k and p are any real numbers and k is known as the coefficient. Alright, so various examples of power functions. We have the constant function. Here, k is, in how I have it written, k is 1, but it could be any number. And p is 0, because this is 1 times x to the power 0. Oops. 1 times x to the power 0. Alright, the identity, x to the first, quadratic, x squared, x cubed, and so on. But what's interesting and what kind of separates us especially from polynomials, which we'll learn about in a moment, is the reciprocal function, 1 over x, is x to the negative 1. The reciprocal squared is x to the negative 2. The square root is x to the 1/2, the cube root is x to the 1/3, and so on. So all of these are examples of power functions, but they're not the power functions we're going to be focusing on. So the power functions we'll be focusing on are the ones that are most related to polynomials. So if we have a power function kx to the n, where n is a non-negative integer, so non-negative integer means we are now removing this side of our list. We're only looking at the left. We're only looking at stuff where we have our positive integer values of our exponent. So to use that, we can now figure out the end behavior of our power functions. End behavior means what is going on, what direction are our arrows facing. So first, we're going to determine whether the power n, which we are now calling n because n is a letter we use for integers, so whether the exponent is even or odd. Then we will determine whether k is positive or negative. So those are the two things we need to think about. Is k positive or negative? Is n even or odd? And then we can use this chart to figure out what our end behavior is. It's as simple as that. So if we have an even power and a positive constant, so for example, like y equal to x squared. We know y equal to 1x squared from our previous chapter means it's going to open upward, so we're going to have our arrows facing both up. Whereas y equal to negative x squared would be facing downward. It has a negative constant, but still that same even power of 2. So we are both facing down. Then here we have y equal to x cubed, for example. Positive constant of 1, but odd power of 3. I will just move over to let you see that. There we go. So we can see x cubed generally looks like that. But y equal to x also looks like that. Y equal to x would look like this, right? Our identity function. So y equal to x cubed, they both have that same directionality to them as we go into their end behavior, as we go off towards infinity. Then on the last one is for a negative constant, like y equals negative x cubed or even y equals negative x, we get it in the opposite direction. So this is essentially x cubed flipped over. So we're going to get we're coming from on the left side we're positive, and on the right side we are negative, or we are heading towards negative infinity. So you'll notice this, what's called arrow notation, that will be introduced later, but essentially what that means is as x goes to negative infinity, f of x goes to infinity. So as x goes to negative infinity, that's this way, as x is going this way, y is going this way, f of x, y, is going towards positive infinity, it's going up. So as x goes to the left, y goes up. Then as x goes to the right, y also goes up. That's essentially what this is saying. So now, what is a polynomial function? We'll get into how that relates to our end behavior in a moment, but we can definitely see how it relates to our power functions, because if n is some non-negative integer, a polynomial function is a function that can be written in the form a n x to the n power, plus, continuing down the line, we can get a n minus 1 x to the n minus 1, a n minus 2 x to the n minus 2, and so on, down to a2x squared, a1x plus a0, all the way down to the constant term. So this is called the general form, or standard form, of a polynomial function. Each ai is a coefficient, ai meaning each of these a's with some number, and can be any real number. So it doesn't have to be an integer, it doesn't need to be positive, it's just some real number. Each product, ai x the I, is a term of the polynomial. Specifically, it is its own little power function. Remember that it is specifically the nicer form of the power functions where we have the non-negative integer n's. So that's how it's related to the power function. It's just made up of a whole bunch of power functions. Then we can say that an, the highest one here, is called the leading coefficient, and n is the degree, making this highest power here the leading term. So it's whatever has the highest power here is the degree, and whatever number is with it is its leading coefficient, all together making the leading term. So if I have 3x to the 5th plus 7x squared minus 12x to the 7th, even though it's not written in the right order, this is actually the leading term because that has the highest power. So the degree is 7, and the leading coefficient is negative 12. So it's not about the order, though we do prefer for it to be in numerical order by the powers. It's just whatever the highest power is. That's what gives us the degree. Then one last note to make about polynomial graphs is that polynomials have graphs that are always smooth, which means they have no sharp corners, and continuous, which means they can be drawn without lifting a pencil. So in other words, they look something like this, but nothing like this, no breaks in them or anything like that. It's just smooth little curvy graphs. That's how all polynomials look. So you can kind of recognize something that's sort of polynomial-like if it's at least smooth and continuous. So looking at some equations, which one of these are polynomials? What are their degree, leading coefficient, and leading term? Well, to figure that out, all we really have to do is make sure we're writing them in general form. That's how we'll find the degree and the leading coefficient, etc. So right now, none of them look like the general form, but we can easily multiply together 2x cubed times 3x in f of x to get it into a general form. So if I multiply 2x cubed times 3x, that's going to be 6x to the 4th. And note that this is only being multiplied by the 3x. These are all that's getting multiplied together. The plus 4 is separate because there's no parentheses, so don't make that mistake. So it's 6x to the 4th plus 4. And so now we can identify what is the highest power here. Well, this is x to the 0 power secretly, and so the highest power is 4. And so this is our leading term. The degree is 4, the leading coefficient 6, and the leading term 6x to the 4th. Then with g of x, again, it's just going to take a little bit of multiplication. I can multiply in my negative x to both terms, so that'll be negative 4x plus x squared, but again, that's not general form. That's not really the direction I want it to be written in, so I'm going to rewrite it. So I'm just taking the x squared and bringing it to the front, just so that I have it in the order I like. Then we have our leading term. The one with the highest power is x squared. So that degree would then be 2, our leading coefficient 1, and our leading term x squared. So even though the original form had the negative 4x first, the leading term is still x squared because we like things to be in numerical order by the powers. But then the last one, Well, now there's nothing really to multiply. I've got this square root of x, which again we learned can be written as x to the 1/2, but 1/2 is not an integer value. So even though it's positive, it's not going to give us a polynomial. So the square root is not an integer power, and so h of x is not a polynomial at all. So we don't care about the leading coefficient or term or degree or anything, because it's just not part of this category. Now looking at some graphs of our of possible polynomials, remember that polynomials are smooth and continuous. So we want to look for which graphs are smooth and continuous. Well, here we can see the two graphs on the left, they are these nice curvy structures, whereas the two graphs on the right, the one on the top, it's pointed. This is probably just an absolute value graph. It's not smooth, so not smooth. And then the graph on the bottom right is not continuous. In order to draw it, I would have to do this and then pick up my pen and then put it back down to draw the rest. So this is not continuous. So that's why only the two graphs on the left could be polynomials. They are specifically polynomials, but not every smooth continuous graph is a polynomial. These just generally look like them, so it gives us a good idea that this is probably one or it's related to it in some way. But of course, this is not necessarily enough information to give us that it's a polynomial. Now, back to end behavior. So, if you remember what I said with power functions, the way it worked for a power function works for a polynomial as well. But now we are treating our leading term as our power function. So the power of the leading term will grow faster than any other term in our polynomial. So that determines the end behavior of the graph. So we can apply the properties for determining the end behavior of a power function to the leading term itself. So here, if our leading term is if our leading term has even degree and has a positive leading coefficient, then we're both going up. So again, this is our 1x squared, and if we have that negative coefficient, our negative x squared or something like that, we're going down on both sides. So even degree means they're both going in the same direction, either up or down. Odd degree, here we've got our x cubed, or just our x, either way, or x to the 5th, or x to the 9th, it doesn't matter. But odd degree, positive coefficient, means they're going in different directions, but we have starting from negative on the left, going to positive on the right. Whereas if we have our negative x cubed, we are now starting from positive on the left and going negative on the right. So let's look at some specific functions. If I have, for example, f of x equals 5x to the 4th plus 2x cubed minus x minus 4, which I realize is a little bit small, but the point is our leading term is 5x to the 4th. So this is positive, even. And so we can look at the graph of it and we can see both sides are going up. Whereas next one, f of x equals negative 2x to the 6th with a whole bunch of other stuff. Our leading term is the negative 2x to the 6th part, though, because again, when we're determining end behavior, all I care about is that leading term. So now we've got negative, even, and so we can see that both sides are going down. So yes, some funky stuff happens in the middle. It's oddly shaped and all of that, and we'll figure out exactly how to tell what that shape in the middle is going to look like later. But really, all we need to be concerned with is the direction of the ends right now. And so, on our next one, we've got our 3x to the 5th, so that's again positive, but this time odd, so we know our ends are going in different directions, specifically because it's positive, we start negative on the left and go positive on the right. Whereas here, with our leading term being negative 6x cubed, that's negative coefficient, odd exponent, gives us positive on the left, negative on the right. So, my best advice for you here is just memorize the easiest forms. So if we go back here, the easiest forms are x squared, negative x squared, x cubed, negative x cubed, or x and negative x if you prefer for the odd ones. Either way, it gets you what you need. Memorize those the easiest ones that you should know what those graphs look like anyway, because they are our common graphs from chapter 1, and that will help you determine help you memorize what the end behavior should look like. Alright, so what about intercepts and turning points? So a turning point of a graph is a point at which the graph changes direction from increasing to decreasing or decreasing to increasing. So here we have two turning points in the graph that's pictured. We started out increasing up until we hit this relative maximum, then we start decreasing down to a relative minimum, and then we start increasing again. So we've talked about relative mins and relative max before. Essentially, turning points occur whenever you have a relative min or max, you're going to have a turning point, because in order for it to change from increasing to decreasing, it has to have turned around. It has to have hit some point and then turned. That's essentially what it's doing, a turning point. The y-intercept is the point at which the function has an input value of 0. We already sort of know that from previous functions. That's always going to be true. But then the x-intercepts are the points at which the output value is 0. So the opposite of the y-intercept. Again, we know about x and y-intercepts, but what's interesting is, yes, finding the y-intercept is still going to be basically the same way as we always have. We plug in 0 to figure it out. But the x-intercepts get a little bit trickier to find when we're dealing with these higher degree polynomials. So, a polynomial of degree n will have at most n x-intercepts and n minus 1 turning points. It will not always have this number, it will have at most this number. So in this case, this polynomial is specifically degree 3. I can say that because I have the function right here. If I were to multiply it out, it would have an x cubed as its leading term and then some other stuff going on. So this is degree 3, which means it has, again, at most 3 x-intercepts. Well, it does have 3, 1, 2, and 3. And at most, n minus 1, so 3 minus 1 is 2 turning points, which it has both of. So it has maxed out its number of x-intercepts and turning points. But it is entirely possible that this graph could have looked like this, and then, or something like that. It could still be degree 3 and look like that. That's fine. Like, the function x cubed looks a little bit nicer than this, but it kind of does that, where it's got the 1 x-intercept and no turning points, and that's fine. The turning points are rounded, and there are no breaks in the graph, so we call this behavior of polynomials being, again, smooth and continuous, respectively. So as I said before, our polynomials are smooth and continuous. The turning points better be smooth. Like, the reason I'm highlighting this another time is because quite often, when graphing, people will forget that we are not coming to a point. Our graph does not look like this and then suddenly turn and then suddenly go like that. It's not pointy, it is round, so it should look round at those points. So make sure when you are graphing these, because you will be graphing these by hand, make sure that you are making them smooth. Alright, so what can we conclude about the polynomial represented by this graph? Well, we can look at the x-intercepts and the turning points to figure out a little bit of information based off of this statement. So a polynomial of degree n will have at most n intercepts and n minus 1 turning points. Again, this is an at most statement, but it still gives us some insight. So we can say, well, there are 2 x-intercepts, right? There are 3 turning points, 1, 2, and 3. We can also say our end behavior, as x is going towards negative infinity. So in other words, as we head towards the left, our y value is going up. And as we head towards the right, our y value is still going up. So we get all of this information. And so that gives us some interesting stuff. First, the 2 x-intercept says that our degree has to be at least 2, because, again, we know a polynomial will have at most n x-intercepts. So if there are 2 of them, We can't have a degree that's less than 2 because that would mean we had too many x-intercepts. So we get degree is at least 2. But the 3 turning points actually tells us that our degree is at least 4. Again, because if it were any less than that, we'd have too many turning points. So we also know that our degree has to be even and our leading coefficient has to be positive due to the end behavior. Can we say any more than that? No, not necessarily. We could guess at what our function is, but this is the most we can say for certain without doing some more work that we don't know how to do yet. So we know our degree is even, we know our leading coefficient is positive, we know our degree is at least 4, so maybe it is degree 4. That could be our answer. X to the 4th could be could be the highest, the leading term of our function, but it could be x to the 6th, it could be more than that, we don't know for certain. Alright. So now, to know a little bit more for certain, we talk about factoring to find those zeros when we have when we're given an equation. So, given a polynomial function f, we want to find the x-intercepts by factoring. So first, I'm going to set f of x equal to 0 because that's the whole point of finding x-intercepts, or zeros, is to set our function equal to 0. So I have my function here, f of x equal to x to the 6th minus 3x to the 4th plus 2x squared. And so it's set equal to 0. Then we are going to, step 1 of factoring is always going to be factor out the greatest common factor. So if the polynomial function is not given in factored form, we start with that. So we factor out our GCF, our greatest common factor. That's always first step. So when I do that, greatest common factor is going to be x squared because I can take that out of every term. So I pull that x squared out, and now I have x to the 4th minus 3x squared plus 2 times x squared. Then I'm going to factor any factorable binomials or trinomials. So this x to the 4th minus 3x squared plus 2, again, this is a technique that was covered in algebra, so I'm not going over it fully in depth here, but this is something that we know how to factor using quadratic factoring. So if you're rusty on this type of factoring, it would be a good idea to look at some factoring review because it is going to come up and you will need to know how to do it. But essentially, we're going to skip ahead and say that we do know how to do this. So using quadratic factoring on this x to the 4th term, I can make this x squared minus 1 and x squared minus 2. And then I can factor these binomials or trinomial. I can factor further is the point, is that x squared minus 1 does actually factor further if I wanted it to. I don't have to necessarily, but this could become x minus 1, x plus 1. And technically this could become x minus square root of 2, x plus square root of 2 if I really wanted to get all of my zeros in there. We don't necessarily have to do that. At this point, if I'm just looking for the zeros, I can find them by setting each term equal to 0. So x squared equal to 0, x squared minus 1 equal to 0, x squared minus 2 equal to 0. Then I solve. So I'm going to add 1 to both sides to get x squared equals 1, x squared equals 2, and x squared equals 0. So x is going to be equal to 0 and positive negative 1, positive negative square root of 2. And there we have all of our zeros, and we can place those on our graph like so. But how did I really know what happened at those zeros? Like, I have these points here. Notice that there's something interesting happening in the middle. I've got all of these, all 5 of these points, right? So here's square root of negative square root of 2, positive square root of 2, 1, negative 1, and 0, but we didn't cross the axis at 0. We still touched it, it's still a 0. But what's going on there, and how did I know to do that? Well, that is because of the multiplicity of 0. So, the zeros of the function to the right, a new picture, occur at x equals negative 3, x equals 2, and x equals negative 1. So, these 3 points, right? But notice that at x equals 2, the graph bumps the axis and bounces back up, just like it did in the previous one, where we bumped the axis and bounced off. So we're hitting it, and then it's basically, it is a turning point. So what does that mean? Well, if a polynomial contains a factor of the form x minus h to the power p, the behavior near the x-intercept is determined by that power. We say x equals h is a zero of multiplicity p. So we have these three zeros. They have three different multiplicities. Specifically, x equals -3 has multiplicity of 1. We can tell this because when we cross through our 0, it's just a straight line through it. We can also tell this by looking at the factored form. So it's got multiplicity 1 right here, x plus 3 to the first power. Then x equals 2 is multiplicity 2. This we can tell because we bounced off. So multiplicity 2, we bounce. And then multiplicity 3, x equals -1, well, essentially it's a little bit different. Multiplicity 3 curves through. So it still crosses across it just the way multiplicity 1 did, but it just does it a little bit curvier. So essentially, the rule that you need to memorize is that zeros with odd multiplicity cross the axis, zeros with even multiplicity bounce off of it. So that's the rule. But we can get a little bit more specific about it. If the odd multiplicity is greater than 1, so like 3 or 5 or 7 or any odd number greater than 1, then when we cross, we do it a little bit flatter. It flattens out in the same way that the graph of just plain old x cubed does. So this is x cubed. So that's one way you can remember is that x cubed does this. And that's essentially what's happening is this is like an x cubed is occurring right there. Because it is x cubed. That's part of that graph. Then at x equals 2 here, we essentially have a graph of x squared. Like that's what's happening. This is the graph of x squared where we bounce off. We hit our axis and we turn around. So that's essentially what's happening. If our multiplicity is higher than 2, it still looks the same. It is a little bit flatter. It just sort of like makes it a little bit flatter than x squared does, but I don't really expect you to get specific about that. So the main things to think about are multiplicity 1 crosses through like a straight line, like x to the first power. Multiplicity 2 bounces off. Multiplicity 3 curves through like x cubed. Multiplicity 4 would also bounce. 5 would curve. 6 bounce. 7 curve. So main rule is odd multiplicity crosses, even multiplicity bounces. And we can tell our multiplicity based on our equation or our factored form. So the fully factored form tells us what our multiplicities are. Multiplicity 1, 2, and 3. But one interesting thing is that the multiplicities here add up to the degree of the polynomial. This is not always the case, simply because you can have complex zeros. If you have complex zeros, it will not add up. But it will never be greater, but sometimes it might be less if you have complex zeros. So, if it adds up, that means you have no complex zeros. If it doesn't, that means you do have complex zeros. So that's just something to think about. But 3, 4, 5, 6, we can say that this is a 6th degree polynomial. Now all of that together, we are now going to sketch the graph of a polynomial. So here I have f of x equal to -2 x plus 3 squared times x minus 5. So it's already in factored form because this would have taken a little bit extra effort to factor that we haven't really learned how to do yet. So that's going to be a future chapter is really going to cover how to factor this type of equation. But for right now, you're given it in factored form. So first step is going to find those intercepts. So luckily, it's already given to you in a pretty nice way. It's given to you in the factored form, so finding the x-intercepts are pretty easy. It's going to be -3 and 5 are our x-intercepts. Then, to find our y-intercept, I'm going to plug in 0. So the y-intercept is -2 times 0 plus 3 squared times times 0 minus 5. So that is -2 times 9 times -5, which altogether is equal to +90. So we get x equals negative 3 and 5, and y equals positive 90. So those are our three intercepts. Then we want to check for even or odd symmetry. In this case, there really isn't any, but we can do that by plugging in negative x. So remember your even and odd symmetry, because that can help with graphing. It can make functions look nice if they happen to have that symmetry. So we can check that by plugging in negative x. But if I do that, I'm going to find that there isn't any symmetry to this one, and that's true of most of our graphs, but sometimes it will look nice. Like, for example, if I go way back here, this one had even symmetry. If I had plugged in negative x into this equation, it would have shown as an even, as an even function, which I can tell because it has all even exponents. That's one way to tell it has even symmetry. All right, so this one, however, does not. All right, now use the multiplicities of the zeros you already found to determine the behavior at the x-intercepts. So we have x equals negative 3. Well, the multiplicity here is 2. So multiplicity 2 means it bounces, whereas x equals 5, multiplicity is 1, so it crosses through. And that's it. Crosses straight through, bounces. Those are our two options, or our two answers. Finally, we will determine our end behavior from the leading term. So I don't have the leading term exactly, but I can find it pretty easily. I just take negative 2 x squared times x. So that's essentially how you're going to get your leading terms, is you'll have a number out front and just multiply it by x to whatever degree it should be. So this is negative 2 x squared times x. That will give me the highest degree of x. So that is negative 2x cubed. So that is my leading term. And so that tells me I have a negative coefficient and an odd degree. So as x goes towards negative infinity, so as x goes towards negative infinity is what this says, f of x, or y, goes towards positive infinity. So as x goes to the left, y goes up. Then as x goes to the right, or positive infinity, y goes down. So finally, we're going to put all of that together. We will start our sketch with this fact. So as we go towards the left, as x goes left, y goes up. So we have this. Then as we go towards the right, as x goes to the right, y goes down. So we look like that. All right. Next, we will put our points, our special points, our intercepts, on our graph, like so. And finally, we will analyze the multiplicities. So we know that we are going to bounce at negative 3, so it's going to look something like that, and we will cross at 5. So let's just bring this all together. It'll look something like this. We'll come through here, and then go down, straight through, and then touch. And yes, obviously, this is not exactly what it's going to look like. Note, does not need to be precise. This has a very crazy scaling, because this is y equals 90 versus this being x equals negative 3 and x equals 5. It's clearly not a good scale. So if we wanted to see what it really looks like, it looks something like this. But we can at least note that x equal to negative 3 and x equal to 5, the behavior worked the way we wanted it to. So this is the accurate graph. But this would get you full credit. If you have each of these special points, you have your multiplicities correct, and you have your end behavior correct, that's what we care about. All of this specific points in the middle, yes, you should test some values to make sure you're correct, but that's basically all you really need, is something that looks rudimentary like this, because it gets you the idea of what it's supposed to look like. And you can plug in to get more accurate values if you need to. All right. Next, we're going to talk about something that's going to feel a little unrelated for a moment, but it does help us a lot. So, the intermediate value theorem. So this is a theorem, special theorem. Let f be a polynomial function. The intermediate value theorem states that if f of a and f of b have opposite signs, then there exists at least one value c between a and b for which f of c equals 0. All right, so that's a lot of words, I realize. But essentially what this is saying is that if I have some graph, okay, and I have a point on the graph. We call this, so here's A, so this is then f of A. And then here's B, and I have a point on the graph, and here's f of B. And so now, f of A and f of B have opposite signs. F of A is negative, f of B is positive. So they have opposite signs. Then there exists at least one point C between A and B. So there's some point C somewhere in here, we'll call this C, for which f of C equals 0. In other words, this point is a point on the line. So basically what it's saying is because this is a polynomial, because a polynomial is continuous. So this theorem is stating about polynomials, but this is true of any continuous function. If I'm coming from here and I go this way, doesn't matter how much I do in the middle, at some point I have to cross through here in order to get to f of b. That's all this theorem is telling us, is that no matter what's going on in the middle, eventually we do have to cross the x-axis to get from positive to negative or negative to positive. So if our values, if our y values, our output values, change from positive to negative or negative to positive, then we have to have had a 0 in between them, because there's no way to get there without picking up my pen otherwise. So it wouldn't be continuous. Alright, so let's look at an example. We're going to show the function f of x equals x cubed minus 5x squared plus 3x plus 6 has at least two real zeros between x equals 1 and x equals 4. So to do this, we're just going to start by testing some integer values. I can plug in x equals 1 and x equals 4, but I can also plug in a few other values to make I'm going to stick with the integers to make my life easy, and then if I have to start picking and choosing other points, I can. I could technically try to factor this, but I'm not going to, because not every function factors nicely. I just need to prove that a 0 exists, so I don't need to factor it. I don't even need to know what the 0 is. I just need to say that it is there. So let's plug in those values. So, when x equals 1, y equals 5. X equals 2, y equals 0. Hey, look, we've just found one of our zeros. X equals 3, f of x equals negative 3. X equals 4, f of x equals 2. Alright, cool. So we found one of the zeros, but we've only found one. And so what are we going to do? Are we going to just randomly plug in points from now on? No. Because again, we don't need to know what the second 0 is. We just need to know that it exists. And we can say that because of these 2 points. So, when x equals 3, so let's see, 1, 2, 3, f of x equals negative 3. So we're here. Then, when x equals 4, f of x equals 2. So we are now here. So some stuff could have happened in the middle, but at some point we had to cross. And so yes, a 0 exists somewhere in the middle. So we can state that we found one 0 specifically at x equals 2, but since we don't need to know exactly what x value the second 0 is at, we can use IVT to prove one exists somewhere. So, because we have that change in sign for our y values from x equals 3 to x equals 4, by IVT, we must have crossed the x-axis, giving us a second 0 somewhere between 3 and 4. We don't know exactly where it is, but that's okay. So, if you are answering a question like this, you should state that IVT is part of it. Don't just say, yes, a 0 exists. You have to explain why. The reason is because of IVT. So say, by IVT, yada, yada, yada. That's an important step in answering a question like this. But again, I never found what the 0 was, and that's okay, because that's not what the question is asking. Now finally, last things we're going to talk about is writing something in factored form. So if we are given a graph of a polynomial of lowest degree, which basically means the lowest thing it can be for what characteristics it has. So there's not something tricky going on. The function can be written as f of x equals a x minus x1 times the power of, to the power of p to 1, then times x minus x2 to the power of p2, and so on down to x minus xn to the power of pn, such that, okay, the graph has all of these x-intercepts, x1, x2, xn, so on. Those powers on each factor can be determined by the behavior of the graph at the corresponding intercept, and then the stretch factor a can be determined given a value of the function other than the x-intercept. So, if we have a graph, if we wanted to write the function given the graph, I start with this base f of x that I had on the previous page. This is just a basic function. And then I'm going to first determine where are my zeros. Well, my zeros are at x equals -3, 2, and 5. So I've now gone down from having p1, p2, pn, all of that. It's now just p1, p2, I guess this should say p3, but it doesn't really matter. So there's only 3 things. There's no dot 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 in the middle anymore. There's only the 3 x-intercepts. So I have all 3 of them. I just now need to figure out what are their powers. Well, that's going to be based off the behavior of the graph at those x-intercepts. So we can see that at x equals -3, we're crossing straight through. Crossing straight through means odd multiplicity. Specifically, straight through means multiplicity of 1. Whereas at x equals 2, we are bumping the axis and then going away from it. So it's a turning point. So turning point means our multiplicity has to be even. Again, we're looking at lowest degree means it's going to be multiplicity of 2, not multiplicity of 4 or 6 or 8. So we're just going with the lowest thing it could possibly be. So multiplicity of 2. And then finally, our last one, again, we're going straight through, no curves. So we have odd multiplicity, specifically multiplicity of 1. So it looks like this. And then I can just take all of this and use it to replace the p-values. So we had p1, p2, p3 are now 1, 2, and 1 again. So our last step is figuring out what is a. Well, that's just going to be based on some point. Again, as I showed in a previous slide, I tend to like using the y-intercept just because there's a 0 in the y-intercept, so it's nice to plug in. So I'm going to take this y-intercept, this point -2, 0, or 0, -2, and plug that in. So we have this point, and I plug it in. So that's going to give me 0 plus 3 times 0 minus 2 squared times 0 minus 5, all times a equals -2. So that's 3 minus 2 squared, so that's 3 times 4 times -5, all times a, which, so let's see, a, 3, 4, -5, still equal to -2. Then all that together is 60, so that'll be 60a equals -2. And then finally, a would be -2/60, or in other words, or -60, sorry, I dropped a negative sign there, but -2 over -60, which gives us +1/30, and so we have our final answer with our a in there. And so now there are no more unknown values except for our x variables, and that's okay. That's what we're looking for. So that's it for our introduction to polynomials. Again, we'll be going over a little bit more about factoring and finding zeros for higher degree polynomials, for more complex stuff. So right now, you just need to make sure you know how to deal with quadratic factoring, because that is not something we go over in depth here, but it is something you're expected to know. So make sure you're practicing that.